This is Ham Nation, episode number 81, January 16th, 2013. The history of single sideband. Hello, everybody. This is K9EID. I'm in Pleasant Hope, Missouri tonight in my news station lab, and boy, what a show tonight. Oh my, just get set. Call your friends, call your buddies. We've been working on this show for about 2 or 3 months. I'm very, very honored to have George W1LSB. We're going to talk about the history of single sideband and about the Central Electronics company and how it affected what all we do today. So, well, we've been working on this for months, and it became such a major deal for us working on this. We're going to split it up into 2 parts. And tonight I'm bringing one of my good friends and a friend of ham radio and all about good old boat anchors with us. And George has some incredible history. We thought we'd bring in the history of single sideband and where it started and how it led up to where we are today. George W1LSB, thank you very much for being here.
Well, good evening, Bob, and thank you for having me, actually. It's quite a pleasure to join you and the Ham Nation viewers tonight and the rest of the crew. You know, you talk about sideband and the history. Actually, I've been fascinated by the subject for quite a long time. I first got licensed in 1958. K1 GXT was my call at the time. KN1, actually. I dropped the N1. I got a technician class license. But at some point, I heard sideband. And by the time I figured out how to decode it or demodulate it, better yet, on my HQ100, I was hooked. It was just something that fascinated me, not to the exclusion of AM, by the way, but it just fascinated me a little bit more. So over my ham career, I've made more of an effort to learn more about it, and much more so recently. And that was probably brought to a head last year. You mentioned the Central Electronics meet, and I know Nick is going to join us at a later date to talk about that more in depth, but it was quite a thrill to meet Wes Shum, who was really one of the originators of sideband in the hobby. But anyway, let's get to does anybody know when sideband originally got started and who invented it? I think it's been published a few times, but if you can go to the slides, it dates back to 1915. A fellow by the name of John Carson, not the comedian. This guy was far from a comedian. He actually got a BS degree at Princeton and wasn't really through at the time. He decided to go on and study a little bit more, came up here to Boston, attended MIT for a little while, went back to Princeton, where he graduated with a master's degree in electrical engineering, and he actually stayed there for a couple more years as a physics instructor. Along about the end of 1913, AT&T knocked on his door and offered him a job. Well, he took it, and thanks to us, or thank you to him, we have something to talk about. Carson was really a brilliant mathematician. He developed a model for eliminating the carrier and suppressing a sideband, and he patented it. Now look how long it took for that patent to go through the process. It was filed in 1915 and didn't get granted until 1923. Of course, anybody that's been involved in FM systems has heard of Carson's name for Carson's rule, which basically states that the bandwidth occupied is equal to twice the deviation plus the frequency, highest frequency of modulation. In this slide, we're looking at Mr. Carson's sideband designs. On the transmitter, it's pretty obvious that he's got a microphone. Actually, this is a diagram right from the patent. You'll see a microphone on the lower left-hand side, a carrier oscillator up on the top, and a balanced modulator. Yes, a balanced modulator, followed by an amplifier. But hey, where's the sideband filter? We'll get into that later. On the receiver, figure 2, an antenna, a coil, an amplifier, a carrier oscillator, a reinsert oscillator, and a simple amplifier. There's some moving parts that are really missing from the diagram, but you get the general sense that this was how it worked. So moving on, Carson's design did have a weakness, and that was when you read the fine print in the patent, you realize that, yes, he could suppress the carrier with a balanced modulator. He'd figured all that out, but the way he tuned out the unwanted sideband was to very carefully tune the antenna, believe it or not. It was done between the transmitter and the antenna. In the antenna, the ACU, talk about ACU, the antenna coupling unit. But remember the frequency these folks used back in those days. Carson was more of a fellow who cared about RF, and the RF frequencies they were using were down around a couple of hundred kilohertz. So getting a high Q tuner wasn't such a big deal. But when you moved up on frequency, you had a lot of problems. So eventually, good sideband filters came along. There were 3 different types: the constant K, the M-derived, and eventually a fellow by the name of Walter Cady came along with a crystal resonator, and a second gentleman by the name of Lloyd Espenscheid put it to work and came up with a lattice filter. And that really cemented filtering sideband. Next slide, please. The phasing method of sideband was developed by none other than Ralph Hartley of the Hartley oscillator. This is a little known fact, and it actually, if you look at the patent, it doesn't say anything about sideband, at least not in the front end of it. It just talks about a modulation system, so it's easy to miss. Hartley was quite a well-educated guy, but he came along, well, I'd say 10 years after the original patent that was filed by Carson, and he filed his phasing method. Let's take a look at what he did. If you start on the left, you'll see the familiar carrier generator going through some phase shift networks and an RF generator going through some phase shift networks. Dual balance modulators, dual amplifiers. There's something really familiar about this. Next slide. Well, when you bring it forward and bring it up to, let's say, the early 1950s, it's identically the same circuit or the same philosophy that was used to develop the central electronics exciters. An RF source that's shifted and an audio source that's shifted through double balance modulators, and that produced single sideband. It's easy to understand how filtering sideband is done. It's not so easy to visualize how phasing sideband is done. So let's take a look at that. In the top diagram, you can see we have a carrier, just an ordinary carrier with upper and lower sidebands, AM for all practical purposes. On the right-hand side, carrier B is identically the same as carrier A. The only difference is that the audio coming out of it or going into the carrier has been shifted by 90 degrees. So that the sidebands are shifted by that same amount. Now, on the lower diagram, we have identically the same conditions, 2 carriers, except this time we're going to shift carrier B by 90 degrees as well. Now remember, carrier B had its audio sidebands shifted by 90 degrees, and now the carrier has been shifted by 90 degrees. And in the next slide, this is where all the magic happens. Okay? The upper and lower sidebands now take on a totally different effect when you combine them. Put them through a set of balanced modulators. Both carriers get canceled out. The lower sidebands in the left-hand diagram will add, and the upper sidebands will cancel because they're 180 degrees out of phase. If you want to produce upper sideband, you just switch one of the audios by 90 degrees and away you go. Simple as can be. Difficult to visualize until you actually go through this exercise. Okay, let's move on. The next real milestone in amateur sideband technology was Bob Moore, W6DEI. Some of you may have heard about this. It was written up in a magazine called R9 in 1933. And this is really fascinating. This guy was a member of the Caltech Radio Club, and he actually published the first article that I've ever found about sideband. It covered 3 different periodicals up between October and January, October of 33 and January of 1934. and it was single sideband transmission for amateur radio telephones. Now, this guy, once you read through his manuscript, once you take a look at his diagrams, you realize he's not just an ordinary ham. He knew a lot more, and we'll find out why next. Look at the design. He starts off with a very low carrier, 10 kilohertz, a balance modulator, a filter, another balance modulator. Actually, he's calling all of these balance modulators in his publication, but they're mixers, in essence. This is a double conversion, single sideband filter transmitter designed in 1933. Well, thinking back to the last slide, what you realize is that Mr. Moore was definitely an employee of the Bell system. And I believe I've been able to track back to the fact that he worked somewhere up in Southern California, actually, around the LA area, and eventually moved to New York. But the interesting thing is, he dropped out of sight. This was the only publication he ever did, and nobody ever heard from him after that. So he did something that was remarkable, had a few transmitters on the air, had a few friends that he worked with, and that was it. All went quiet for quite a while after that. Remember, in 1933, the comet hadn't even, the Hammerland comet hadn't even come out yet. Think of the stability issues that he had to deal with. It was quite a feat. Moving on. From 1933 to 1947, there really wasn't a lot of activity. There were some articles put out about single sideband phone by a fellow by the technical editor of QST, and also by a fellow by the name of J.L.A. McLaughlin, who also was fairly prolific in writing. But his system, when he said single sideband, he wasn't thinking of suppressed carrier. He was just thinking of an AM system having dual sidebands and being able to reduce one of them or take one of them away and make room for more people on AM. That's all. In fact, Millen brought out a sideband adapter, which was nothing more than that, just a selective receiving filter that would switch from upper to lower sideband, but it did not have a product detector and it did not have a BFO. However, in 1947, the world changed. September 21st, W6YX was on the air on sideband, run by Mike Villard, W6QYT. That was the beginning. Next. Mike was quite a guy. Stanford University, PhD, one of the founders of Stanford Research. The timing couldn't have been more perfect. Once he had started that first test, it really caught on like lightning. And he got such a reputation that Wes Shum actually hired Mike as a consultant early on to help him start Central Electronics and to get things off the ground. Next. 1948. If you go back and look in QSTs, those of you that have access to the QST archives, you'll see every single one of these articles in there. It starts off, and this was really a break for QST, for the league. 3 articles in January 1948, including the results, exactly what happened during the Stanford tests, and on down throughout the year, up to the very end. Just a profluence of sideband articles. Now, that started quite a rush of people to make stuff, to make it work. It caught on, people wanted it, people didn't want to build it, they wanted commercial things, so this started quite an avalanche. And you can see here how many people had really early sideband gear to be able to purchase. Central Electronics was certainly among the earliest in 1952. Elenco was another, and Eldeco was another yet. They all got on. Central, I think, was one of the ones that really lasted the longest of the very earliest. You can see Gonset, Hallicrafters, Johnson, Lakeshore, P&H, they all had something really interesting. Gonset didn't make a transmitter, but they did make a sideband amplifier. Next. Now, Central Electronics started, I believe, in 1951, but the first advertisement in QST didn't really hit till 1952. When we hear from Nick, we'll hear a lot more about the history of CE, but these are the products they made starting in 1952, and everything was a phasing transmitter, by the way. They never made a filter rig. The 10A, 1952, was a single 6AG7 phasing network. It was a coil-operated rig. When I say coils, you had to pull a set of coils out to change bands. That was the only way it changed. And there was a further improvement of it in 1954 that used a later chassis, and it had a few more features, but basically it was the same. In 54, they came out with a band switch version that had twice the power. The 10A meant 10 watts PEP out. The 20A had 20 watts PEP. But the difference was the 20A was a bit more sophisticated in that it had a band switching arrangement. No more chugging and plugging the coils. And again, it had twice the power, a pair of 6AG7s in the final. Now, the 458 VFO was actually a modification of one of the surplus command sets, a BC 458. Take a few parts out, put a few parts in, and you have a very stable VFO at 5 megs. Remember, these are 9 megahertz phasing exciters. So you take 9 megahertz and you beat 5 against it. On the minus side, you get 80 meters, 3.8. On the plus side, you get 20 meters, 14 megs. And to do anything else, you have to beat a different frequency against your 9 meg exciter, and that's exactly what it did. It had multipliers in there. The next and the biggest, no, can we go back to that one? Thank you. Down at the bottom, there are 2 really dramatic developments that even stand today as remarkable. The 100V exciter, you take a look at it, that's all you had to do. There was no tuning. You'll see on the left, there's an audio gain. You can see the band switch, and you can see a few other controls, but you can't see a load and dip control. There's a couple of little doors there in the bottom. They have things like mic gain, power control, power output, etc. But the function switch, the calibration set, it was full broadband on every band, 10 through 80. And some of them even had 160 in there. An amazing, truly amazing 100-watt transmitter. The other amazing thing they did was to come up with a 500-watt, actually it was a 600L, 600 watts input with a single 813, fully broadband linear. Bob made a comment the other night. It has 2 knobs, a band switch and a meter switch, and that's it. Put 5 or 6 or 7 watts into it, and you get an input of about 500 to 600 watts. It's an extremely well-built linear amplifier. It's got automatic VSWR protection, automatic plate current protection. It's built like something that came out of the factory just a couple years ago in terms of its capability and its features. Okay, now we can move on. Now, to go with these transmitters, West built an awful lot of different accessories. The scope. This was a monitor scope that went in line with your exciter and your amplifier and ran a comparison. So you could take a look at the envelope. You could take a trapezoid or an envelope pattern and look at it and get a really good, careful look at your modulation. The 10-meter adapter in the middle was for the CE458 VFO to give you 10 meters with a very stable crystal oscillator in there. A compression amp, a Q multiplier. The sideband slicer was really very common and very popular. There were 2 models, the Model A that didn't have the Q multiplier, and the Model B shown there with the Q multiplier built in. And they were built for 455 kilohertz IFs. If you didn't have 455, you had adapters that would mix up or down to give you the 455, like the APs. Okay, next. Now, just for comparison, this was the only phasing receiver adapter available. It was a GE design, and it was something that West built a later design around, not exactly this model, but a slimmed down version of it. This was designed by Don Norgard, W2KUJ, who worked for GE. But look at that price. In 1948, you would have had to pay $275 for this sideband selector. It was synchronous, by the way. There is a synchronous button on it. But by comparison, an HRO7 was a little over 300, a 129X just a little under 200. And the infamous, or famous actually, SX42 was only a few dollars more. So to get on sideband and to do it commercially was going to cost you some money back in those days. Okay. Now a few thoughts about Wes. to wrap it up here. In my humble opinion, in those days, in that time, Central Electronics made the most sophisticated single sideband exciters you could buy. Sure, there are a lot of competitors out there. At the little meeting we had, I asked Wes who he was most afraid of as competitors, and he said, I wasn't afraid of any of them. And you know what? He was right. He was right about phasing. If you look at QST articles, last couple years, you see phasing is coming back. Look in the web, you'll find a couple of different exciters. QRP phasing exciter. Some of the biggest names in amateur radio are now using phasing generation. And that just proves to me that Wes really was right. And to wrap it up, I'd just like to personally thank Wes and all the people that are still out there that worked with him to help bring the hobby to where it is now and make a difference. Thanks, Bob. Back to you.
What a great presentation. That's so great. And I know all the guys in Texas. I just got off the net before this with K5LYN with his 200V, and he runs a net. Everybody should write this down: 3870 on 75 meters at 7 o'clock on Wednesday night, right before Ham Nation, and on Sunday, 14292. Lynn runs these vintage boat anchor nets, and he uses Central Electronics, and you hear a lot of it on there. Talk to you next week right here on the Twit Network. Ham Nation, this is K9EID. Bye-bye for now.